So I think let's go ahead and get started. Thank you everyone for coming to the LPI virtual seminar this week. Our guest this week is Crisotope of the Paris Globe Institute of Physics, and he'll be talking about the chromium isotopic insights in the early solar system. So please take it away. Thank you so much for being here.
Yes, hello everyone. I'm very happy to give this presentation. And this work is almost done my PhD thesis. Firstly, I want to thank the following colleagues from this from the following institutions. And I also have to thank the funding organizations for providing my living expenses and the research costs. And a special thank to NASA Johnson Space Center for providing me some precious meteorites. And my presentation will be divided into like several parts, like a general introduction, the analytical methods, and the science part. And I mainly study the chondrites and the chondrules and some terrestrial planets. First, and this is the nebula, after the condensation, and we have the chondrites, like the different chondrite parent bodies, and inside the chondrites we will have the round igneous spheres, and they are chondrules, and they may contribute to the operation and differentiation of the terrestrial planets like Earth, Mars, Ureilite, Angrite, Vesta, aubrites, and these planetary bodies. However, there are several fundamental questions we need to answer, like when and how did chondrules form? When and how did the planets and asteroids differentiate? And what are the genetic relationships between chondrite parent bodies and the terrestrial planets? We are very lucky because we have the meteorites samples from these different bodies in the solar system. You know, I'm mainly doing the chromium isotopes, so I must explain how can the chromium isotopes work. Chromium has 4 isotopes, and their abundances are as the number shows. The first mechanism is radiogenic. That is, the 53 manganese can decay to 53 chromium with a half-life of 3.7 million years. And here we use the epsilon 53 chromium to represent the radiogenic chromium isotope. And then the 54 chromium is a nucleosynthetic or anomalous isotope. And this figure is to show the solar system materials. They have variable epsilon 54 chromium values. For example, the carbonaceous chondrites, they have the positive values, and Earth and asteroid chondrites, Moon, they have the 0 values, and ordinary chondrites and other differentiated meteorites, and they have negative epsilon 54 chromium values. And here we use epsilon 54 chromium to represent the nucleosynthetic anomalies. But a bad thing is the chromium isotopes will be modified by the cosmogenic effect, and the galactical cosmic ray will react with the iron nickel metal to induce the ingrowth of all the 4 chromium isotopes. Finally, and I also study the mass-dependent chromium isotopes. And chromium is a siderophile and volatile element, so it can be used to trace the planetary differentiation processes like volatile depletion, core formation, and magmatic processes. And here we use delta 53 chromium to represent the mass-dependent chromium isotope fractionation. Here I must mention 2 papers. The first one is this paper, and the author Louis Break, and he is a colleague in IPGP, and he firstly observed the ingrowth of the radiogenic 53 chromium. And also Anne Tunke from IPGP, and she is the PhD student of Jan-Louis Brick. And she firstly observed the epsilon 54 chromium, the nucleosynthetic anomalies in different solar system materials. And this opens a new field for the study of nucleosynthetic anomalies like titanium, calcium, zirconium, and many other isotopes. So we can see that there is a epsilon 54 chromium dichotomy between carbonaceous and non-carbonaceous meteorites, and this can be caused by slow line migration with time or the Jupiter formation. Now I will introduce which kind of events can be dated by the manganese chromium chronology. And the first is the magma crystallization, because the different minerals have varied manganese chromium ratio. Then the volatile process, that's because manganese and chromium possess different volatility. Then the planetary mantle-crust differentiation, that's because manganese and chromium possess different compatibility, with chromium entering the crust and with manganese entering the crust and chromium residing in the mantle. And finally, is the aqueous alteration, and that mostly occurs in chondrites. That's because the carbonates are possessing very high manganese chromium ratios. So we can achieve some in situ analysis. And this slide is about mass-dependent chromium isotope. For the left figure, we can see that all these chondrites, they have a similar chromium stable isotope composition as the bauxite Earth that is represented by the gray bar. This suggests the co-formation, the terrestrial co-formation will not fractionate chromium isotopes. And the right figure mainly shows the chromium stable isotope difference between Moon and Earth, the two blue bars. And the isotopically light chromium in the Moon relative to Earth indicate chromium evaporation during lunar magma ocean stage. And this is different from other isotopes like zinc, potassium, or gallium. And all these elements, the Moon is heavier than the Earth. Now let's go to the analytical method. For the mass-independent chromium isotope measurements, and I used a 4-step column chemistry. This is a bit slow, but this complicated purification is mainly to achieve a high yield chemistry. That's because the chromium the chromium isotopes will fractionate on the columns if the yield is not high enough. And we can use both TIMS and MC-ICP-MS to measure the mass-independent chromium isotopes. And the TIMS consumes less sample, while MC-ICP-MS gave better precision. And for mass-dependent chromium isotope measurements, and we use the double spike techniques. Firstly, we add the 2 spikes to the sample and just pass through a easy column, the two-step column, and with a slightly lower yield, but it doesn't matter because the chromium isotope fractionation can be corrected by the double spikes. We can also use both TIMS and MC-ICP-MS to measure the mass-dependent chromium isotope fractionation. And normally, and I use 20 volts to measure them to get a better precision. It's like 0.02 per mil for a 2SD uncertainty. It's the science sections now, and firstly I will introduce chondrites, and they are the sediments of the solar system, and the chondrules, which indicates the dynamics of early solar system, and the planets where support the lives. chondrites are the oldest cosmic sedimentary rocks and the most pristine of which preserve information about the origin of solar system. Chondrites contain the chondrules matrix and also some refractory inclusions. It's like CEIs and AOAs in the middle figure. Bark chondrite samples have chemical compositions that have been taken as proxies for the composition of bark differentiated meteorites, such as ours. Thus, investigating the chemical and isotopic compositions of chondrites is central to better understand the evolution of the solar system and planet formation. Let's first focus on the epsilon 54 chromium, the nucleosynthetic anomalies. And this figure clearly shows that there is an epsilon 54 chromium sequence for chondrites. It's as this sequence. So, and we should note that CV and CK chondrites with similar oxygen isotopes, petrology, but distinct epsilon 54 chromium values. So they do not derive from a same parent body. And the CB, CH, CO, CM class have similar epsilon 54 chromium values, suggesting they are created at similar conditions. And this Ureilite chondrites, they have EC and Earth-like epsilon 54 chromium values. And the Kakungari chondrites, this gray circle, it has ordinary-like epsilon 54 chromium values. And we can also see the ungrouped carbonaceous chondrites, the red triangles, and the ungrouped non-carbonaceous chondrites, the blue triangles. And all the ungrouped CCs have epsilon 54 chromium values more than 0.3, and all the ungrouped NCCs have epsilon 54 chromium values less than 0.3, confirmed the isotopic dichotomy. And we should also see that there was some intragroup epsilon 54 chromium variations in CB, CR, CM, CO, and CV chondrites. This may result from a sample heterogeneity or just the heterogeneous accretion of their chondrite parent bodies. After the epsilon 54 chromium, and we should also see the epsilon 53 chromium, the manganese chromium systematics in chondrites. And the left figure is some literature data, and they show that all the carbonaceous chondrites form on the same manganese chromium isochron, and this isochron dated the condensation time of the solar system. But we can see this isochron is mainly rely on this point, and that is a CB chondrite. And then I did the panorama of chondrites, and I found the CB they are not as low as the previous data suggest. And in the middle figure, I see that just the colorful circles, and there is no manganese chromium isochron for all the carbonaceous chondrites. And I think this is because chondrites possess different nucleosynthetic anomalies, so they may have different origins. And then chondrites are complicated assemblages, and all these components may also have different formation time and modes. We know that like CEIs and chondrules, maybe they do not always form at the same time, and we don't know the formation time of the matrix. However, when I combined all the data for all different kinds of chondrites, we can see a positive trend between manganese chromium ratios and epsilon 53 chromium values. I think this is most reflecting a mixing between high manganese chromium and low manganese chromium reservoirs, and this is most mixing line and low time significance. After chondrites, and I also studied the chondritic components, the chondrules. Chondrules are millimeter-sized silicate spheres with igneous textures as the major components of most chondrites. They are like this, and they are very old. chondrules are one of the oldest objects in the solar system, and they record the history of the early solar system. And also, chondrules may be the potential building blocks for terrestrial planets. And for my study, I mainly did the two kinds of chondrules. One is EH, and the other one is CO. Instantite chondrites, we know that they have similar isotope compositions for most elements to the Earth-Moon system. Also, instantite chondrites possess similar water content as Earth. So it is promising that Earth and Moon originated from instantite chondrites. And instantite chondrites also have similar chemical composition and oxygen fugacity to Mercury. So their chondrules are promising candidates as precursor analogs of the solids that operated to form the Earth, Moon, and Mercury. We know there were different kinds of dating systems like uranium lead and aluminum magnesium, but the chondrules, the size of the chondrules in instantite chondrites, they are very small, and they cannot be dated by uranium lead. And also there were too much there were too much non-radiogenic lead in the insect chondrules, so we cannot use uranium lead system. And previous study also found lack of aluminum-rich minerals and no radiogenic magnesium excesses in aluminum-rich chondrules in instantite chondrites. For CO chondrites, they have the most refractory inclusions, and also due to the size problem, and uranium lead cannot be dated by, the CO chondrules cannot be dated by uranium lead. Before I show my magnetic chromium ages, and I want to explain the different chondrules. They have maybe different time significance or different isochrons. First is the uranium lead, and the leaching method, and they dated one single chondrules, and this is an internal isochron, may reflect the last melting age. And that is similar to the aluminum magnesium dating. They also dated one chondrules with different mineral phases, and this is also an internal isochron and reflecting the last melting age. And for hafnium tungsten, and they date both chondrules, or like the poor chondrules, and also they plus the matrix materials. I think this is mostly mixing and do not have any time significance. And finally is our magnetic chromium dating, and we dated several chondrules. And this is an external isochron, and should date the chondrule precursor formation and the volatile events for the chondrule precursors. Just two tips, and the ages dated by external isochron should only be older than or similar to internal isochron ages. Then it makes no sense to compare the external isochron ages with internal isochron ages to test the distribution of initial 26 aluminum in the solar system. I may just have some comments on this paper. So these two figures are my magnetic chromium age. The first is EH chondrules, and this yellow circle, or this orange circle is iron rich. I think maybe it is contaminated by some sulfide, so I didn't include it in my isochron. And these blue two ones, and they have anomalous epsilon 54 chromium values. I also did not include the two yellow circles. And all the red normal EC chondrules and the bulk EC chondrite, they show this age. It is 1.7 million years after CEIs. And for CO chondrules, and they are very old, they have similar age to CEIs. And in the right figure, I combined all the uranium lead ages and the magnetic chromium ages here. And the uranium net edges are diamonds, and the magnetic chromium edges are shades. So I found maybe there are like 3 episodes for chondrule formation, and the first one is the normal silicate chondrules, maybe from CO, CV, CR, and ordinary chondrites. They formed simultaneously with CIs. Then the insertite chondrules, and they formed 1.7 million years after CIs. And finally, is the metal-rich chondrules, maybe CB and CH chondrules, and they formed very late, 4.8 million years after CIs. These 2 figures are showing the epsilon 54 data for chondrules. And the left figure is about CO chondrules. We can see they have heterogeneous epsilon 54 chromium values that are correlated with epsilon 53 chromium values, maybe suggesting some chondrule precursors from CI formation region, and this region should be very hot, were transported to carbonaceous chondrite occlusion region. And the red figure, and we can see the 2 anomalous ones. Some insertite chondrules, they have the CC-like epsilon 54 chromium values. So maybe this suggesting an inward transportation from CC occlusion region to EC occlusion region. So finally, when we combined these 2 projects, maybe there is a picture for the chondrule formation and early solar system dynamics. Here is the sun, and here is a proto-sun maybe, and close to the sun, it's the CI formation region, and the CIs and the epsilon 54 chromium carrying phases with very high melting point, so the firstly condensed. And there should also have a compensating material, and the silicates, they condense later and without the epsilon 54 chromium carry phase. And this region is the CO chondrite formation region, and they are far from the sun. And the materials from CI formation region can be transported to the CO chondrite occlusion region, and they mixed with the matrix material in CO chondrite occlusion region, and this low magnetic chromium ratio and low epsilon 54 chromium values materials mixed with the CC matrix material with high magnetic chromium ratio and high epsilon 54 chromium values. So they finally formed the epsilon 54 heterogeneity in CO chondrules. And for the EH chondrules, maybe some material from the CC occlusion region can be inward transported to the EC occlusion region and contaminate the EC chondrules. So there are like both inward and outward transportation processes occur in the early solar system. Also, I think this transportation model do not support the chondrule, and the matrix have the same origin, or we say the chondrule matrix complementarity. The section 5 is about the planets, and I will mainly introduce the 6 different planets. The first is Earth. I mainly use chromium isotopes to study the early volatile depletion of the proto-Earth. And the Angrite parent body, the Angrite is the titanium-rich planet, and also the Ureilite parent body. In the Ureilite is a carbon-rich planet. And the aubrites, aubrite is very reduced and have the strong relationship to insertite chondrites. And Vesta, and this planet has already observed by our spacecraft, I think. And finally, it's about Mars. Okay, this figure is combined with the epsilon 54 chromium isotopes and the mass-independent oxygen isotopes. We can see that different solar system materials have they formed at different regions for these 2 isotope indexes. So the combined chromium and oxygen isotopes can be a very robust tracer to trace the origin of the solar system materials. I think for some planets, it's like a Vesta and a Ureilite parent body. It may need the unknown chondrite reservoirs with more negative epsilon 54 chromium signatures for their precursors, because like in this region, there's no chondrites. Okay, for Earth, and my observation here is that okay, firstly, I introduced the variation of the chromium isotopes for the terrestrial samples. We can see there is a correlation between epsilon 53 chromium and epsilon 54 chromium values for terrestrial samples. And this could be caused by some non-kinetic mass-dependent fractionation of chromium isotopes on teams or in the terrestrial magmatic processes. From the two bars, and the black bar is representing the epsilon 53 values for chondrites, and the gray bar represents the epsilon 53 chromium values for bark Earth. We can see there is a clear epsilon 53 chromium difference between chondrites and bark Earth. And they also have different manganese chromium ratios. We know that manganese is more volatile than chromium under reduced conditions in nebula, and which is also consistent with the decreasing manganese chromium ratios from chondrites to Earth. So based on the epsilon 53 chromium and the manganese chromium difference between Earth and the chondrites, there should be a volatile process for proto-Earth happened only in 0 to 3 million years after solar system formation. And I also used the chromium stable isotope to study the chromium loss on Earth. Yes, and we can focus on the two bars. The blue bar represents the average chromium stable isotope composition for insertite chondrites, and the gray bar is for bark silicate Earth. And previously, we have already known that co-formation does not fractionation chromium isotopes, and which is also consistent with the RB initial calculation. And finally, we interpret this delta 53 chromium deficit may be caused by a volatile loss at equilibrium chromium isotope fractionation. And this is similar to the Vesta and the Moon story. But we know the Earth is very large. So the gravity will not allow the volatile loss. So I think this volatile loss should happen during the planetesimal magma oceans. And this story is also consistent with the heavy magnesium in Earth relative to chondrites and to this Nature paper. And we should also see that there are three small circles, and they are the chromium stable isotope composition for insertite chondrules. And they are also heavier than the insert chondrites, so may reflect a volatile loss at a reduced nebula environments. And now let's go to the Angrites. Angrites are differentiated achondrites coming from the terrestrial planet, Angrite parent body. They can be divided into volcanic Angrites and plutonic Angrites. Angrites have homogeneous oxygen isotopes and are the most volatile depleted among the planets in the solar system. And we can see the figure is the x-axis is the potassium uranium ratio, and the y-axis is the rubidium strontium ratio. And both rubidium and potassium are more volatile than strontium and uranium. So this figure is mainly show the volatile depletion degree for the solar system bodies. So we can see the Angrites are extremely depleted volatiles. Also, the significance for Angrites, it is the Angrites are chosen as the time anchor for the short-lived isotope dating systems like aluminum, magnesium, manganese, chromium, and hafnium tungsten chronometers. This figure is to show the epsilon 54 chromium systematics for Angrites, and all the Angrites, they have homogeneous epsilon 54 chromium values, and this contradicts the previous study, and that is mainly this paper, and they show the Angrites have variable epsilon 54 chromium values. And I think the homogeneous epsilon 54 values for Angrites also consistent with their homogeneous oxygen isotope compositions, and this isotope homogeneity suggests magma ocean, the global scale magma ocean on the Angrite parent body. The epsilon 54 chromium values for Angrites are very similar to the ordinary chondrites, but they cannot originate directly from ordinary chondrites because they do not share the same titanium, calcium, and oxygen compositions. And this figure is the manganese chromium bulk isochron for Angrites. And this H dates the Mantle-Crust differentiation for Angrite parent body. We know the mantle always have low manganese chromium ratio, and the crust has high manganese chromium ratio. And this manganese chromium ratio is also correlated with the magnesium number, the magmatic differentiation index. And this figure is we also compared all the internal isochron ages, and the blue diamonds are uranium lead age, and the red circle are manganese chromium age, and the purple triangle is hafnium tungsten age. And the Angrite parent body formation is represented by my bulk isochron age. Here is the orange bar. And from this figure, we can see that all the uranium lead, hafnium tungsten, and manganese chromium ages are very consistent. So this suggests the parent nuclide hafnium and manganese homogeneity in the solar system, where we see at least in the Angrite parent body region. We can also compare the ages for the differentiation of Angrite parent body, the orange bar, and the formation of volcanic Angrites, the red, here, and the formation of the plutonic Angrites in the lower part. And so I think the significance for the Angrite external and internal isochrons are similar to those of chondrites. It's like the bulk, or we say the external isochron for Angrites is also my work, and they date the differentiation of the Angrite parent body, and the internal isochrons for Angrites, they dated the crystallization of the single Angrite meteorite. And I think this age difference for all the Angrites may indicate a cooling history of Angrite parent body. The volcanic Angrites crystallized and cooled very fast, and the surface with the formation of the Angrite parent body's crust, then the plutonic Angrites cooled deeper and slower inside the Angrite parent body. And now we turn to Ureilites. Ureilites are primitive achondrites and rare mantle rocks for terrestrial planets. They can be divided into monomicted Ureilites and polymicted Ureilites. And there are another asteroid named Almahata Theta, maybe also from Ureilite parent body. The size of Ureilite parent body is highly debated, which might be as large as Mars or very small. And the Ureilites are carbon rich. 3% maybe can have up to 7% of carbon in it. And as primitive achondrites, unlike other differentiated planets, Ureilite parent body possesses heterogeneous oxygen isotopes and that are correlated with the iron manganese ratios and magnesium numbers is made from the right figure. For my data and my high precision data show Ureilites, they have a clear epsilon 54 chromium heterogeneity in Ureilites. And this suggests the Ureilite parent body did not experience global scale magma ocean. And in this figure, the blue circles and the blue squares, they are from the literature data. So I think it's mainly because their precision are not high enough. So before they did not distinguish this chromium isotope heterogeneity. And the average value for all the monomixed Ureilites is minus 0.9, are lower than all the chondrites. And we also suggest the carbon rich, or we see the carbonaceous Ureilites are not derived from carbonaceous chondrites, although Ureilites are carbon rich and have similar oxygen isotopes as carbonaceous chondrites. And there is a broad relationship between magnesium number, chromium isotopes, and iron manganese ratios. And these correlations may indicate Ureilites were mixed between two reservoirs. And then we use manganese chromium to date the age of the two reservoirs. And this is the manganese chromium isochron. And we know that the heterogeneous epsilon 54 chromium values suggest the age does not reflect a global differentiation. So from the correlation in the last slide, and this age should firstly date the separation of the two Ureilitic reservoirs, and this orange square is a precious chunky andesite from Ureilite parent body, and that maybe can suggest this isochron also dates the partial melting process on Ureilite parent body. And here is some nickel isotope data. So for the left figure, we can see like all the Ureilites, the nickel stable isotope composition for Ureilites overlap with all the chondrites, and the red bar are carbonaceous chondrites, green bars are ordinary chondrites, and the blue bars are ancestral chondrites. And their similar nickel isotope composition suggesting the planetary co-formation process do not fractionate nickel stable isotopes. And we also did the chromium stable isotopes for Ureilites. And it's here, Ureilite parent body. Ureilite parent body possesses heavier chromium stable isotopes than chondrites that's represented by the gray bar. So this can be induced by a sulfur-rich co-formation process. The 5.4 part is the aubrites. Aubrites are the group of igneous achondrites, and they are primarily composed of iron-poor insertites, and are often called insertite achondrites. And aubrites have similar petrology, oxygen-filled gaseous, and isotope compositions to insert chondrites and the Earth-Moon system, and they are also have some similar things to Mercury. And my work show firstly we see the epsilon 54 chromium values, and all the like different insertite achondrites, and they fall into three different groups. And the first one is the main group, insertite achondrites, and it's the main group aubrites, and the shallow water aubrites, and finally the I don't know how to pronounce the name. It may be the Isotopic. And there were three groups for the epsilon 54 chromium values. So maybe this suggests and all the insertite achondrites formed from at least three parent bodies. But here we should note that maybe their oxygen isotopes are not sensitive for their origins because all the interstellar chondrites, they have similar oxygen isotopes. This figure is shows the chromium stable isotopes, and all the three interstellar chondrite parent bodies, they possess isotopically heavier chromium than the chondrites. And this maybe suggests a sulfur-rich conformation for their parent bodies. And here is the Vesta. And Vesta is a small planet, and it experienced the core mantle-crust differentiation. And we believe that the Howardite, Ureilite, diogenite meteorites come from the Vesta. And Vesta also differentiated very early, and this is dated by manganese chromium chronometer. And the HED are also depleted in volatile elements, and its position is here. In this work, I mainly do the chromium stable isotope compositions for Vesta. And first we see there is a correlation between chromium content and delta 53 values. And also there was some correlation between magnesium number with the delta 53 chromium values. So this is a clear magmatic processes fractionate chromium stable isotopes. And the Vesta has isotopically lighter than chondrites, and mainly the ordinary chondrites. And this chromium stable isotope difference between Vesta and chondrites should mostly be caused by a volatile process. And this story is similar to the Moon and the difference between Earth and the interstellar chondrites. And this chromium equilibrium isotope fractionation should happen at a relatively low temperature, maybe under 2,300 Kelvin. So this is consistent with magma ocean mechanism rather than the giant impact model for the volatile depletion of Vesta. And finally, let's go to the Mars. I'm sorry, maybe I will need another like 3 minutes. And Mars is the fourth outward and the third biggest terrestrial planet in the solar system, which might be habitable for human beings. Understanding the origin of Mars is fundamental not only for itself, but also providing important analogs for origin of Earth and other rocky bodies and essential insights into the early evolution of solar system. However, now we do not have like real Martian samples, and we only have the Martian meteorites. Until now, there were total 317 Martian meteorites were observed, and they can be divided into 5 types or maybe 6. The sugarite, nacrolite, chalcignite, this orthopyroxenite, and the breccia. And this figure is the breccia NWA7034, and that is also called the Black Beauty. And here is my high precision mass independent chromium isotope data. So we can see there is a resolvable chromium isotope heterogeneities for both epsilon 53 and epsilon 54 in Mars. It is not consistent with the previous homogeneous epsilon 53 data, but the data in this paper, they are made by teams, are not as precise as my data. And we should also see that Mars possesses higher epsilon 53 chromium values than Earth. This suggests a higher magnetic chromium ratio of proto-Mars. And we know that Mars is less volatile depleted than Earth. And only in reduced conditions, manganese will be more volatile than chromium. Therefore, the proto-Mars are more reduced than Earth. To introduce this chromium isotope heterogeneity on Mars, and I just have this kind of story. So first, Mars started to accretion and experienced the magma ocean, mostly heated by the aluminum mechanism decay system. And Mars also experienced the Mantle-Crust core differentiation, and this should happen very early based on the lutetium and hafnium dating. So, and after the Mantle-Crust differentiation, and the Martian crust has high manganese-chromium ratio, higher than the mantle. And so in result, a crust has higher epsilon 53 chromium values than the mantle. And then I think for most of the planets, and there is a net accretion processes. And these green ones, and they are carbonaceous chondrite materials. And they always have high chromium content than the planetary crust, and also high epsilon 54 chromium values than Mars. And these materials falling to Martian surface and contaminate the Mars crust, and makes the Martian crust also has higher epsilon 54 chromium values than the mantle. And then maybe there is an impactor cause remelting processes and results in the mixing of primordial Martian mantle and crust. So in this way, and there is a correlation between epsilon 53 and epsilon 54, and the chromium isotope heterogeneity for Martian meteorites. And the left figure is the Martian crust dichotomy. So maybe this impact also caused the Martian crust dichotomy, and maybe also the two Martian moons, the Phobos and the Deimos. Okay, and my presentation is finished. So the final note is that we can use chromium isotopes to get some timing information, origin information, and the process information. So thank you very much. I'm happy to take any questions.
Awesome, thank you very much.
Yeah, thanks.
And it's sometimes a little bit difficult to get a sense for the audience appreciation in these online settings. So if you enjoyed the talk, please let Kit know in the chat. We do have a question that came up during the chat from Serena Goodrich. Did your manganese chromium dating indicate that CC chondrules formed 0 million years after CAI, or that their precursor materials formed then?
Yes, and this is a good question. It's like the time significance between the manganese chromium dating and aluminum mechanism dating, or we say the Ureilite. Yes, and my manganese chromium dating can only date the chondrule precursors, and but this precursor age should always be older or only similar to the last melting age of chondrules. Thanks.
Also, if you'd like to ask a question directly, you can use the raise your hand feature, and I will ask you to unmute your mic. In the meantime, we have another question from Xiaofan. Very interesting talk. A few things I don't quite follow. One, do you know the parent phases or minerals of 54 chromium in chondrites? And what are the silicate minerals you mentioned that formed in the CAA forming region, but with complementary compositions to CAIs? Well, we'll start addressing them one at a time, then I'll ask the second question after.
Oh yes, I think I prefer to first answer the question. Okay. And yes, and the previous studies, they use the SIMS, the nano SIMS, to detect the how to say, the residues from Ci chondrites, the acid residues from Ci chondrites, and they find the very tiny particles, maybe only several nanometer, and they are extremely epsilon 54 chromium rich. So mostly it's like this tiny phases, maybe they are chromites, these tiny chromites, and they cause the epsilon 54 chromium variability in chondrites. Oh, okay. And then you ask the CI formation region. Oh, okay. Yes. I just imagined in CI formation region there is a compensating reservoir for CIs because when the CIs they are only the calcium and aluminum oxides, but most of our inner solar system bodies is made by silicates. So I imagined maybe there should be a silicate reservoirs in CI formation regions. Then, and you say not sure the types of chondrite samples you analyze, but they do they show any textual evidence for chromium or terrestrial? I think this answer is no, and currently we did not find the relationship between petrology and chromium isotope compositions. Thanks.
Cool. Serena Goodrich has a comment. The metal in Ureilites may not be indigenous or not totally indigenous. It may not be useful for dating metal silicate fractionation on the Ureilite parent body. Do you have any comments on that?
Yes, the metal in Ureilites may not be indigenous. I think yes, maybe there are some arguments say that the metal in Ureilites can be from the core. But I also consider this question, and we know that the carbon in the smelting process of Ureilite parent body, the carbon will react with olivine to produce some metal from the mantle composition. So I think maybe most of the metal in Ureilites and they are from the mantle, and it may not be useful for dating metal silicate. Yes, and that is also a possibility for the manuscript age for my for the Ureilites from my work. Thank you very much.
Do we have any other questions from the chat? Again, feel free to raise your hand if you're more comfortable asking the question directly. Okay. As you see, some very nice comments in the chat about yeah, those were fantastic. Yeah, very well put together presentation. Absolutely, very clear. Even I can follow it, and I know very little about isotopic systems.
Thank you. Yeah.
Well, if we don't have any more questions, we can go ahead and let you guys go for the day. Thank you so much again. This was a really great talk. Really appreciate you coming out here.
Yeah. Yes, I also want to thank the invitation from NASA Lunar Planetary Institute again. And thanks for giving me this opportunity to show my work. Yeah.
Absolutely.
Yeah.
It's our pleasure. All right. Thank you very much, everyone. There's no LPI virtual seminar next week, but we will release an announcement when we have the next one scheduled. So please keep your eyes open for that. Thank you very much and have a wonderful afternoon.
Yes, you too. Bye. Bye-bye.